Welcome back, my fellow radiation nerds! Today we dive deep into the radioactivity and uses of Krypton-85. Krypton is a colorless, tasteless and odorless noble gas, and it was first discovered in 1898 by William Ramsay and Maurice Travers. It has an atomic number of 36, and its most common isotope is Krypton-84, which is stable. Krypton-85, on the other hand, is radioactive, and it was first discovered in 1940 by Martin Kamen and Sam Rubin during their research involving neutron bombardment of stable krypton isotopes at the University of California, Berkeley. Krypton-85 is a radioactive isotope with a half-life of approximately 10.76 years. It decays through a beta emission, transforming into stable rubidium-85, and in the process it also releases a gamma ray with an energy of 514 keV. Krypton-85 is predominantly produced through human activities, such as nuclear fission and the reprocessing of spent nuclear fuel. However, traces of Krypton-85 are also produced naturally by the interaction of cosmic rays with stable Krypton-84, found in Earth's atmosphere. Some of the main uses of Krypton-85 are in arc discharge lamps and in cold cathode voltage regulator electron tubes. Since Krypton-85 is a gas, it can also be used to find leaks in closed systems and small defects in aircraft components. My sample comes from an old DDR smoke detector, produced by Robotron RFT. The model number is 70130, and in the past it was used in industrial complexes. The actual radioactive source is a little glass bulb, originally containing 18.5 megabecquerels of Krypton-85. Since the detector is a couple of decades old by now, the activity of Krypton-85 has decreased, but it is still detectable when measured with my RACID gamma spectrometer. When placed on the top of the detector, RACID showed an activity of 136 CPS and had no problem in detecting the peak at 514 keV. The housing of the smoke detector acts like a shield, and it stops most of the beta radiation, which results only in a slight increase in the activity when measuring it with my Ludlum Model 3 meter with a 44-9 probe. This, however, changes when the housing is removed and the glass bulb is exposed. At 5 cm distance, my Ludlum reads 500,000 CPM, and it maxes out if brought any closer. RACID reads a gamma dose of 0.86 microsieverts and activity of 675 CPS at 1 cm distance. Overall, I'm very happy to finally get a chance to explore the radioactivity of Krypton-85 and share my experiences. I absolutely love the shape and form of the source, and I find it very interesting that this smoke detector uses Krypton-85 instead of the much more common Americium-241. If you ever come by one of those detectors, they are a great find, but be careful as the glass bulb is rather fragile and can easily break. Welcome back, my fellow radiation nerds! Today we dive deep into what really happened at the Bayo Canyon. Bayo Canyon is located east of Los Alamos, and it is a place of striking natural beauty. With its breathtaking landscapes, towering cliffs, and vibrant wildlife, one might assume this area has been a peaceful retreat forever. But in the 1940s, a series of powerful explosions shocked this place, leaving behind a legacy that endures to this day. During the Manhattan Project, a team of scientists was tasked with studying the behavior of radioactive materials under extreme conditions. Their work was critical to the development of the plutonium implosion-type bomb, just like the bomb Fat Man, which was later used over Nagasaki. A total of 242 tests were conducted, with each test using several hundred curies of radioactive materials, primarily radioactive lanthanum-140, often referred to as RALA, which has a half-life of just 40 hours. However, lanthanum was not the only radioactive element used. These tests continued until 1961, and in 1976, the government initiated a cleanup of the area, burying the radioactive contaminants deep underground. Yet, to this day, debris can be found around the location of the test site, with some pieces still exhibiting traces of radioactivity. Today, the Bayo Canyon has slightly elevated activity, though I'm not sure if it's from the contamination from the test or from natural sources, as I've recorded the same increased activity pretty much throughout my entire hike to the location of the test site. During my exploration of the canyon, I discovered around 2 dozen pieces, including metal shrapnel and cable wiring. When inspected closely, you can see how the intense force of the explosion tore the metal apart with ease. From all the pieces I found, one appears to be radioactive, and clocks around 2000 CPM on my Ludlum Model 3 with a 44-9 probe at 1 cm distance. This discovery was particularly intriguing, given that all radioactive lanthanum-140 should long be decayed. Curious to uncover its source, I conducted a gamma spectrum using my raced gamma spectrometer. The analysis reveals peaks at 63, 93, and 186 keV, which are characteristic for uranium. Given the small size of the peak at 186 keV, it's likely that the sample contains depleted uranium instead of the regular one, as the uranium-235 was in high demand for the production of the uranium bomb Little Boy, which was later used over Hiroshima. If you find yourself in Los Alamos with some time to spare, I highly recommend hiking through Bayo Canyon. Whether you're a nuclear physics enthusiast or a casual tourist, the canyon offers stunning natural beauty, diverse wildlife, and a unique glimpse into the history of atom bomb development. The hike is about 1.5 hours one way, so make sure to bring plenty of water and prepare accordingly. Hi! Radioactivity is all around us, but how do we actually measure it? You probably heard people talk about sieverts, curies, becquerels, counts per minute, and many other types of units. But which ones should we actually use? Most units can be put into two categories: activity units and dose units. To measure the activity of radioactive objects, we use units called becquerels, where 1 becquerel is equal to 1 decay per second. If you're located in the US, you're probably more familiar with using curies, where 1 curie is equal to the activity of 1 gram of pure radium-226, which is 37 billion becquerels. Many radiation meters use counts per minute, CPM, or counts per second, CPS, instead of using becquerels. This is because these units show the exact amount of radiation decay events detected by the Geiger tube, or scintillator used by the meter. Depending on the type of detector, its sensitivity will vary, meaning that some can show 200 CPM while others can show 1000 CPM for the same source. When it comes to the Geiger detectors, one of the most commonly used by the scientific community is the LND 7311, which is often found in pancake-style probes such as Ludlum 44-9. The activity units are the best way to measure how active an object or an area is. The most common dose units are sieverts and rems. Rem stands for Röntgen equivalent men, and 1 sievert is equal to 100 rems. Both sievert and rem are used to measure biological effects of ionizing radiation on human tissue. Sievert is a SI unit, while rem is a part of the older centimeter-gram-second system, or CGS for short. Similarly to the case with becquerels and curies, sieverts are used in most countries around the world, while the US still sticks with rems. Some Geiger counters, such as Therapy, show the readings only in dose units, as they have been designed to be used in nuclear contaminated environment and quickly inform the user about the dose they are being exposed to. These readings can be widely inaccurate when measuring radiation coming from other isotopes to which the meter has not been calibrated to, due to the differences in gamma ray energies coming from the different isotopes. Here's an example. Most Geiger counters are usually calibrated for cesium-137, which has gamma energy of 662 keV. Americium-241, on the other hand, has an energy of 59.5 keV, while cobalt-60 has energies of 1173 and 1332 keV. This means that the dose emitted from these isotopes won't be presented accurately when measured with a Geiger counter that has been calibrated for cesium-147. Some Geiger tubes are gamma compensated, and will show more accurate results even when used to measure isotopes outside of their original calibration source, such as the case with the CDV-700 Geiger counter. When measuring samples, it is important to keep a distance between the source and the detector. This ensures accuracy and consistency, as it adheres to the calibration standards and minimizes errors from scattering and absorption. Furthermore, it optimizes the detector's sensitivity and efficiency while reducing the risk of contamination and accidental exposure, ensuring reliable and safe measurements. Personally, I always try to give measurements in counts per minute, which I get on my Ludlum Model 3 meter with a 44-9 probe attached to it at a 1 cm distance from the source. This way I can ensure that the results are accurate, consistent, and comparable between different tests. Sometimes I also include a dose rate in microsieverts per hour, which I measure using my raised gamma spectrometer, which factors in the different gamma energies of isotopes being detected. Welcome back, my fellow radiation nerds. Today we will learn about the radioactivity and uses of terbium-161. Terbium is a rare earth element with an atomic number of 65. It has only one natural occurring isotope, terbium-159, which is stable. Terbium has been discovered in 1943 by a Swedish chemist, Carl Gustav Mosander, who is also the chemist behind the discovery of lanthanum, which radioactivity and uses I already covered in an earlier video. Since terbium is part of the lanthanide series, it shares many of their chemical and physical properties. Terbium-161 is a short-lived radioactive isotope of terbium, and it is produced by the irradiation of stable gadolinium-160 in the PRISMAP network of research nuclear reactors. It has half-life of just under 7 days, and it decays for a beta emission into stable dysprosium-161, and in the process, it also releases gamma rays at 25.7, 48.9, and 74.6 keV, which my rayset had no problem in detecting. My sample of terbium is in the form of terbium chloride solution, and it has an activity of around 100 to 150 becquerels. On my raised gamma spectrometer, I got only 16 CPS when measured inside of my lead castle, with the sample being placed as close as possible to the detector. The soft beta radiation coming from terbium-161 unfortunately is being shielded by the plastic container, and I got only marginally higher activity compared to the background radiation, when measured with my Ludlum Model 3 meter with a 44-9 probe at 1 cm distance. Terbium-161 is currently being tested for use in nuclear medicine to treat prostate cancer and in imaging techniques such as single-photon emission computed tomography. While I don't have much time with this sample before it decays, it was great fun measuring its radioactivity and learning about it. I'm curious to hear your thoughts on terbium-161 and what did you find the most interesting about it? Let me know in the comments below. Welcome back, my fellow radiation nerds! Today we're diving deep into the radioactivity of ancient dinosaur fossils. During my recent trip to United States, I visited the meteor crater, which was an absolutely amazing experience. After the tour, I went to the souvenir shop, where I spotted some megalodon teeth. I heard before that sometimes they can be radioactive, so I quickly took out my therapy Geiger counter, and I got very excited when my meter started showing increased levels of radiation. Of course, I couldn't leave without taking one home, and here I am. I was curious to what isotope made the tooth radioactive, so I used my raised gamma spectrometer to create a gamma spectrum which revealed that the tooth contains natural uranium. While the activity isn't particularly high compared to something like uranium ore, it's definitely detectable and reads about 1000 counts per minute on my Ludlum Model 3 with a 44-9 probe at 1 cm distance. So now you're probably wondering, how does a fossil become radioactive? During the process of fossilization, the organic matter is being replaced with the surrounding minerals, and if those minerals contain radioactive elements such as uranium, the fossil can absorb them and become radioactive over time. This isn't just limited to megalodon teeth either, it can happen to all kinds of fossils. For example, at the Grant Mining Museum in New Mexico, there are several dinosaur fossils with significant radioactivity due to them being fossilized in a uranium-rich environment. Speaking of the Grant's Uranium Mining Museum, I highly recommend visiting it if you're gonna get a chance. There's a lot of fascinating information and exhibits in it, and the underground tour was a truly unique experience. I used to be a guide in a uranium mine, and I found it particularly interesting to see how uranium mining techniques compared between America and Eastern Europe. Thanks to the decay of radioactive isotopes, scientists can estimate the age of different fossils. This process is known as radiometric dating, and some of the most commonly used isotopes are carbon-14, potassium-40, and uranium-238. Exploring the radioactivity of my megalodon fossilized tooth was a lot of fun, and I have learned a lot while at it. I'm curious to hear, do you have any radioactive fossils in your collection? Or maybe you didn't know that fossils can be radioactive and now you will measure them? Let me know in the comments below. Welcome back, my fellow radiation nerds! Today we will explore the radioactivity of a noble gas that is the second leading cause of lung cancer, Radon-222. During my recent trip to United States, I visited a couple of famous uranium mining sites, including Mi Vida and Cotter mines. There, I have collected a few samples of the local uranium minerals, and while the radiation coming from those samples might be a bit high when measured up close, it is important to remember that those are point sources, and with distance the activity quickly drops back to normal levels. Furthermore, the plastic boxes I keep the samples in prevent the spread of any particles and pieces that might have fallen off the main mineral. However, what concerns me is not the radiation coming from the uranium minerals, but the gas emitted by them called radon. Radon-222 is a naturally occurring radioactive element with an atomic number of 86. It is part of the uranium decay chain, directly being produced by the decay of radium-226. It was first identified in 1899 by Ernest Rutherford and Robert B. Owens at the McGill University in Montreal, making it the fifth radioactive element to ever be discovered. It has a half-life of 3.8 days, and it decays into polonium-218 through an alpha emission, with an activity of 5.67 petabecquerels. What makes radon particularly dangerous is its possible buildup inside of buildings, as it escapes from underground as a result of natural uranium decay. Its detection is challenging, as radon is a noble gas and it doesn't have any smell, taste or color, and can only really be detected using specialized equipment. This results in radon gas being one of the leading causes of lung cancer, second only to smoking cigarettes. Furthermore, radon decay products can easily attach themselves to anything they come in contact with. This includes clothes, different surfaces, and lungs if inhaled. While the half-life of radon is only 3.8 days, it decays into toxic heavy metals, including polonium, thallium, and lead. This means that if inhaled, these elements will remain in the lungs and eventually be absorbed by the body. In some countries, radon tests are mandatory for residential and public buildings, and the levels should generally not exceed 300 becquerels per cubic meter, although WHO recommends to keep the levels below 100 becquerels per cubic meter, and EPA recommends action if the radon levels exceed 148 becquerels per cubic meter. If you have a ventilation system with air filters inside of your building, you can do a simple experiment and check the filters for radon using a Geiger counter. I did that at my parents' place, and their filters clearly showed increased levels of radiation. This is perfectly normal and should be nothing to worry about, as long as the radon levels inside of the building are within recommended limits. A gamma spectroscopy of an active carbon sample that has been exposed to radon gas shows an interesting spectrum. While it is similar to uranium or radium spectrum, it clearly misses few peaks from isotopes found higher in the decay chain. Here's a gamma spectrum of a uranium ore sample for comparison. As you can see, the peaks from uranium-235 at 144 keV and radium-226 at 186 keV are missing. Now you may wonder, I have a Geiger counter, can't I use it to measure radon? Well, technically yes, but it's actually a little bit more complicated than that. While a Geiger counter can detect radiation coming from radon and its decay products, it is not an ideal tool for detection of radon gas or measuring its concentration. In order to do that, a dedicated radiometer must be used, which is specifically designed for this purpose and will give precise, long-term measurements, which are essential for evaluating potential health risks from radon exposure. In order to keep track of the radon levels at my home, I reached out to the amazing guys over at ARNet, who have kindly provided me with their Radon Plus and background radiation meters, which have inspired and made this video possible. The meters look great and have very nice elegant design, and they both use e-ink displays, which I'm personally a big fan of as it looks fantastic and consumes very little energy, allowing them to run for multiple years on just 2 AA batteries, which come included in the box. The initial setup and connecting the meters to the allRadioactive phone app was a piece of cake, and the app allows you to get much more insight about the data being recorded. Both meters are fairly compact and have the same width and height, however they do differ in their depth, as the Radon Plus meter uses an ionization chamber, which requires extra room compared to the pin diode detector used by the background radiation meter. If you want to learn more about those meters, make sure to check out the allRadioactive website or the YouTube channel. Coming back to my concern about the radon levels, after setting up both meters, I allowed them to run for a few days so that they could calculate an average measurement. When I checked the allRadioactive app, I saw that the readings for radon concentration were around 30 becquerels per cubic meter, depending on the time of the day, and the background radiation hovered at around 0.1 microsievert an hour, which is more than acceptable and within the recommended limits. Realistically, having just a few small uranium minerals should not cause any significant increase in radon levels, but I'll continue to monitor the readings just in case, especially since winter is coming and ventilating my home isn't as easy as in summertime. Although I haven't measured any significant levels of radon at my home, this might not be true for everyone. If your levels are elevated, the easiest solution is to simply ventilate the room more often. In some extreme cases, more drastic measures have to be taken, which can include sealing off the basement floor or installing an active ventilation system, but I recommend consulting a specialist first before taking any action. If you're a collector of uranium minerals, radium watches, or other items that can produce radon gas, a radon meter is definitely a must. This being said, if you live in an area that is known to have high levels of radon concentration, investing in a radon meter is definitely a good idea. The team at allRadioactive has also provided me with a special discount code for all the viewers of the channel, so if you decide to buy a meter from allRadioactive, make sure to enter allRad5 at checkout, which will give you additional 5% off from your order. Alternatively, you can also use one of the links in the video description. Thank you allRadioactive once again for providing me with the meters and making this video possible. I'm curious to hear about your experiences with radon. Do you live in a high radon area? Do you use a radon meter? And how do you control the levels at your home? Let me know in the comments below. Welcome back my fellow radiation nerds. Today we will take a closer look at the Bayo Geiger S2 meter and if it's really a Bayo Geiger counter. Geiger counters are one of the most common tools used for measuring radiation all around us, but they are not perfect. They often suffer from limitations such as inaccurate dose rates and low sensitivity, which are characteristics of the Geiger-Müller tube used by the meters. In the recent years, there has been a surge in products that use small scintillation crystals instead of the more traditional Geiger-Müller tubes, but they are usually more advanced devices targeted at experienced users, not entry-level amateurs. This is where the Bayo Geiger S2 comes in. First things first, I would like to thank Robert from Bayo Geiger, who was kind enough to provide me with the S2 meter, making this video possible. The Bayo Geiger S2 is a personal radiation detector manufactured in Colorado, USA. It is made out of high-quality plastic which feels solid and durable, and for extra protection the unit is wrapped in a rubber case which should prevent it from any fall damage if it would slip out of hand. While slightly on the bigger side, it can be operated single-handedly, and navigating through the menus and settings was pretty simple and intuitive. Despite its name, Bayo Geiger does not use a Geiger-Müller tube. Instead, it has a small scintillation crystal which gives about 100 counts per minute of background activity. Unlike most Geiger counters, Bayo Geiger factors in the different gamma energies detected to give accurate gamma dose readings. The measurements can be displayed as microsieverts per hour, millirem per hour, and counts per minute. And the unit does also have an alarm feature, which threshold can be adjusted to the user's preference. While it can detect some strong betas, it's not particularly sensitive to them, and I think it is better to think of the meter as gamma only. When compared to my other meters, the Bayo Geiger showed much higher sensitivity to gamma radiation, which I think can be particularly helpful when looking for radioactive minerals. I got a few uranium hunting trips planned, and I'm very excited to take the meter with me and see how it performs. I really did enjoy using the Bayo Geiger S2 meter. However, I do see some potential improvements for future versions to make it even better. Firstly, the plastic used over the display screen is way too soft, which makes it very easy to scratch. I would love to see it replaced with one that is more resistant to wear and tear of everyday use. Secondly, I would move the sensor to the top of the meter. At the moment, it is facing the user, making it hard and impractical to measure different sources, as it's not always easy to see the readings on the screen. Thirdly, I would like to see an improved version of the algorithm which would quickly adjust the readings when there's a sudden increase in activity, but then stabilize once the correct measurement is reached. The one currently used is definitely not bad and does the job pretty well, but it would make the unit faster and more responsive. So, is it worth it? Considering the unit is priced at just under $150, I think it is a good alternative to many meters in the same price range. I love the fact that it shows accurate gamma dose readings and that it has higher sensitivity to gamma radiation than conventional Geiger counter. While it's not the perfect tool for everyone as it doesn't detect beta radiation very well, I still think it is a solid meter, offering something new and unique to the market. I want to hear from you. What are your thoughts on the Bayo Geiger S2 meter, and do you have any experience with it? Let me know in the comments below. Welcome back, my fellow radiation nerds! Today we'll take a closer look at the radioactive contamination inside of my lead pick container and try to identify the isotope behind it. Lead picks are lead containers used to store highly radioactive sources and shield the radiation to help minimize exposure. This one in particular originally came from one of the German nuclear power plants, and it is made out of solid lead and weighs about 2 kilograms. Although the container did not come with any radioactive sources, after unboxing the package I noticed that the inside of the container emitted radioactivity and was most likely contaminated with some mysterious radioactive source. This discovery was very exciting, and I was very curious to find out what isotope was behind the contamination. There are plenty of different radioactive isotopes out there. Some of them are natural, such as uranium, thorium, and their decay products, and some of them are man-made, produced in nuclear reactors, particle accelerators, or during atomic tests. In order to find out what isotope is behind the contamination, I need to narrow down my search and eliminate any isotopes that don't match the characteristics and properties of the one inside of the lead pig. I'll start by checking what type of radiation is being emitted from the container. First, I'm going to take a measurement without any shielding, and then I'll start introducing different materials to block out different types of radiation and compare the results. For this purpose, I will use my Ludlum Model 3 with a 44-9 probe, as it can easily detect alpha, beta, and gamma radiation. Alpha particles can travel in air up to 5 cm and can be easily stopped with a thicker piece of paper. Beta particles can travel in air up to half a meter and can go through low-density materials, but a piece of aluminum should be enough to block them. Gamma rays can travel very long distances, and they are the hardest to shield, requiring very dense materials such as lead or even sometimes uranium. From my first measurement without any shielding, I got a result of about 1000 counts per minute at 1 cm distance. After placing a piece of paper between the probe and the container, the result remained unchanged. This meant that there are pretty much no alphas being emitted by the source. Next, I've added a piece of aluminum, and the readings dropped significantly, all the way back to background levels, meaning that the source was a primarily beta emitter, and even if there was some gamma radiation, it was extremely low and not detectable by my meter. Although I haven't detected any gamma radiation above background levels, I still decided to run gamma spectroscopy with my RaySeed. Sometimes even a trace amount of gamma radiation is enough to build a good gamma spectrum and identify different isotopes. Inside of my lead castle, the background activity is only 1.2 counts per second when measured with my RaySeed gamma spectrometer. After placing the lead pig container inside of my lead castle, I got a reading of 3.5 counts per second, and after collecting data for a couple of hours, I've managed to create a gamma spectrum of the lead pig. The gamma spectroscopy revealed peaks that are characteristic for uranium ore. I spoke with the previous owner and he did mention that he stored uranium ore inside, so there's definitely a big chance that a small piece of the mineral broke off and now sits at the bottom of the container. However, the amount of beta radiation compared to gamma could hint at another contaminant, but unfortunately I don't have the tools to properly check or identify it. This is actually not the first time I see a contaminated lab equipment. A friend of mine has a lead pipe that is contaminated with radioactive cesium-137 as a result of a chemical spill inside of it. I wanna hear from you. Did you ever find some contaminated lab equipment? And do you think the remains of the uranium ore are the only contaminant inside of my lead pipe, or could there be something more to it? I'm looking forward to hearing your suggestions and answers in the comments below. Welcome back, my fellow radiation nerds. Today we dive deep into what is arguably one of the best radiation meters out there, the Ludlum Model 3. The Ludlum Measurements Incorporated was established in 1962 by Don Ludlum. Not long after, it has produced its very first commercially available meter, the Ludlum Model 2. Ludlum's official YouTube channel has a very interesting video on one of the very first units ever made, with a serial number of 31, which I have linked in the description below. His meters quickly gained popularity and good reputation for their reliability and long use life, which quickly established Ludlum Measurements as a trusted name in the world of radiation detection. The success of the initial models paved the way for the development of a wide range of survey meters and radiation detection equipment that continues to be used around the world to this day. Ludlum meters are the go-to meters for many scientists and first responders because of their extremely rugged, reliable, and easy-to-use design. Furthermore, Ludlum Measurements offers a wide range of probes and accessories which can be easily swapped out for various applications. Adding the long and proven track record, it is easy to see why Ludlum meters became the preferred choice for scientists worldwide. If you look at the Ludlum's product range, you will quickly realize that there are a bunch of different models out there. However, for personal use, I think these are the ones worth considering. If you want to learn more about different Ludlum models, I encourage you to read the detailed description on the Ludlum website. The Ludlum Model 3 has a range from 0 to 500,000 CPM and can supply voltage to the probe between 400 and 1500 volts. This flexibility allows it to work with a variety of different detectors, including scintillators and some neutron detectors. Most of the time I pair my Ludlum Model 3 with a 44-9 probe. However, I do change that occasionally depending on the situation. The meter features a rotary switch for selecting different measuring ranges and performing a battery test. It also includes both slow and fast averaging modes, which are particularly useful for obtaining accurate readings in varying conditions. Powered by 2 diesel batteries, the Model 3 offers approximately 2000 hours of use. The batteries are housed in a separate compartment, which helps to protect the electronics from potential damage in case of battery leakage. Additionally, all parts of Ludlum Model 3 are sealed to prevent the moisture from entering the meter, enhancing its durability. These features clearly demonstrate that Ludlum meters are built to last and why they have earned their stellar reputation. I acquired my Ludlum Model 3 a few years ago, and it has been my primary meter ever since. It has a serial number of 104, 163, and it has been manufactured on April 16, 1992. Despite its age, it operates absolutely flawlessly, having only small scratches from regular use. In order to ensure accurate readings, I calibrated my unit using a pulsar made by Geology. If you're interested in learning how to calibrate your meter, I recommend watching this video. My unit has a meter face showing only counts per minute. If you have seen my previous video on how to measure radioactivity, you know I am not a big fan of those units when it comes to measuring activity of samples, so this works perfectly for me. Ludlum does offer different meter faces for different probes, however I would still recommend sticking with the counts per minute. Originally my meter came with a C-type connector, which is common on most Ludlum devices. However, this connector is hard to come by in Europe, so I replaced it with a BNC connector. This modification made it much easier to find compatible cables and probes. The meter also came equipped with a set of latches for a strap, which, while I don't use very often, they are a nice and handy addition for prolonged use, as the meter weighs over 1.5 kilos and can get heavy over time. Lastly, I crafted a probe holder for my 44-9 probe from a sheet of metal. While it's not aesthetically pleasing, it gets the job done. I'm also thinking about adding a check source holder to the side of my meter. However, I can't seem to find one for a good price. If you know where I can get one, let me know in the comments below. So you want to buy a Ludlum meter. Congratulations, great, but where do you find one? If you're set on a brand new meter, you can purchase one directly from Ludlum website. However, be aware, their prices are generally aimed at labs and government agencies, not private individuals. A new Ludlum Model 3 will run you about $1,000, and that's without any additional accessories or probes. In my opinion, it is a far better choice to buy used or refurbished unit online. Labs occasionally clear out their old inventory, and it is the best time to find used meters and probes at a relatively low price. I got my meter during one of those sales, and I paid only a fraction of what I would pay for a new one. When evaluating a used meter, ensure it is in a good visual condition. No dents, corrosion on battery ports, or cracked glass. Ludlum meters are mostly analog, meaning they are very easy and inexpensive to repair if any internal parts would fail. This being said, I noticed that newer Ludlums are made with PCBs which use those micro components, which are much harder to work with unless you have proper tools for them. Ludlum is not the only company producing high-quality radiation meters. Brands like Eberlein or Johnson also offer fantastic meters that are worth checking out, often at a lower price than a Ludlum. For example, I found my Eberlein 120 meter, which is similar to a Ludlum Model 2, that came with a pancake probe and a check source holder for a whopping £110, and that's including international shipping. Good deals are out there. You just need to be patient and keep an eye out for them, and then eventually one will pop up. Ludlum meters are the industry standard for a reason, and I highly recommend checking them out. Their professional build, high performance and great versatility is what led me to purchasing one for myself, and I have absolutely no regrets. I'm curious to hear what meters are you using for your measurements. Do you have, or are you planning on investing in a Ludlum meter? Let me know in the comments below. Welcome back, my fellow radiation nerds! Today we will explore the radioactivity and the geology of the most common thorium mineral, monazite. Monazite is a brownish phosphate mineral, primarily known for containing several of the rare earth elements, including lanthanum, cerium, and thorium. It scores between 5 and 5.5 on the Mohs scale of mineral hardness and has a density of 4.6 to 5.7 grams per cubic centimeter. Compared to other thorium minerals such as thorionite or thorite, monazite contains much less thorium at around 6 to 7%. However, its widespread availability makes it the most common thorium ore, accounting for approximately 12 to 15% of the world's total thorium reserves. Monazite is most often located in placer deposits of sand and gravel. It's primarily found in countries like India, Brazil, South Africa, and Australia, but can also be found in many other places around the globe. Monazite is not a single mineral, but rather a group of minerals with very similar structure and properties, but with slightly different dominant elements. There are several variations of monazite, with 5 main types. 3 of these variations contain radioactive thorium, while another 3 contain lanthanum, which does have a naturally radioactive isotope of lanthanum-138, but its radioactivity is extremely low and generally difficult to detect, especially in the presence of thorium. Since monazite is rich in rare earth elements, it has been their primary source for many years. In the 1880s, Karl Auer von Welsbach was looking for a supplier of thorium to produce his newly invented thoriated gas mantles. One day he noticed that Brazilian ships use monazite sand as ballast, and soon Brazil became a key supplier of thorium for the production of his gas mantles. For many years, Brazilian and Indian monazite dominated the industry. However, after World War II, much of the mining activity was shifted to South Africa. Unfortunately, due to radioactive waste produced during monazite processing, it was eventually phased out in favor of bastonite in the 1960s, which contains much less thorium, making it safer to work with. In the recent years, the growing interest in thorium reactors as a potential alternative to the uranium reactors has sparked renewed interest in thorium. This shift could lead to increased demand for thorium and possibly bring monazite back into commercial use. I acquired my sample during a recent mineral show. It's the most common variation of monazite containing cerium, and it comes from Madagascar. Despite its small size, its radioactivity is easily detectable, reading at around 2000 counts per minute on my Ludlum Model 3 with a 44-9 probe at 1 cm distance. Although I already knew from its chemical formula that thorium is present, I decided to do a quick gamma spectroscopy with my recent gamma spectrometer just to be sure. As expected, it revealed peaks characteristic of thorium-232 and its decay chain. I'd love to hear about your experiences with monazite and other thorium-containing minerals. Do you have any in your collection? And what other minerals should I cover in the future videos? Let me know in the comments below. Welcome back, my fellow radiation nerds! Today we will explore the radioactivity and the nonsense of some more quantum science scalar energy quackery items sold on Amazon. If you enjoy this content, make sure to subscribe to my channel so you don't miss any of the upcoming uploads. Thanks, and now back to the video. In the past, I explored the radioactivity of two quantum energy pendants, and in both cases they have turned out to be radioactive due to the thorium content. Since then, most of the listings have been taken down, but occasionally they do pop up every now and then on websites such as Amazon. Recently, I was browsing through the internet and I found some quantum energy stickers, which I haven't really explored before, so I decided to order them and see if they will be radioactive. The first sticker was marked as anti-radiation sticker that will protect the user from harmful 5G radiation.
Right.
The definitely not photoshopped stock photos on the listing recommend placing the sticker on all electrical devices such as phones, tablets, laptops, and TVs. Despite the stickers being marketed as anti-radiation, I measured a pretty decent radioactivity coming off of them. When measured from the front, I got a result of 250 counts per minute and 700 counts per minute when measured from the back of the sticker at 1 cm distance with my Ludlum Model 3 with a 44-9 probe. I'm guessing that the silicon layer blocks some of the alpha and beta radiation, resulting in lower activity when measured from the front of the sticker. I was curious about how the sticker was constructed and which part in particular made it radioactive, so I used my trusty Swiss knife to peel its layers one by one and conduct a little autopsy of it. The sticker is made of 3 parts: silicon top, shiny middle part, and a sticky brown layer at the bottom. After measuring each part separately, I found that the brown bottom layer was the radioactive one. The second sticker was marketed as Advanced Technology, Scalar Energy, Energy Savior, Made in Japan, Anti-Radiation Protection, yada yada yada. And surprise surprise, when measured with my Ludlum Model 3 with a 44-9 probe, I got a reading of over 2000 counts per minute at 1 cm distance. However, this time I decided not to dissect the sticker as it seems to be made out of a single piece. The two pendants I explored before do contain radioactive thorium-232, and I was curious if that would also be the case with these stickers. To find out, I conducted a gamma spectroscopy with my racist gamma spectrometer, which revealed that both stickers contained radioactive thorium-232 and its decay products. Thorium or monazite is pretty common in China. In fact, it is much more common there than uranium, which is why China is currently investing heavily into thorium breeder reactors. I'm assuming that thorium is a waste product of monazite processing, as monazite is rich in several other rare earth elements, but I have absolutely no idea why it's being added to those stickers. I guess it at least makes a pretty cool check source for all of us nuclear nerds. While those stickers are a pretty cool and relatively safe source to handle, their marketing is very misleading, and they definitely should not be sold on Amazon or similar websites under the current description. Just remember that some people still believe in tinfoil hats. Welcome back, my fellow radiation nerds! Today we're diving deep into the world of gamma spectroscopy and how can we use it to identify different radioactive isotopes. If you enjoy this content, make sure to subscribe to my channel so you don't miss any of the upcoming uploads. Thanks, and now back to the video. Gamma spectroscopy is a technique used to identify and analyze different radioactive isotopes based on their characteristic gamma energies that they emit. Although this technique has been around since the early 20th century, it is only after World War II that the technology began to improve, particularly with the development of scintillation crystals, which allowed scientists to perform more detailed analysis of gamma-ray spectra. By the 1970s, advances in semiconductor technology led to the creation of detectors such as high-purity germanium detectors, which resolution far surpasses what can be achieved with traditional scintillation crystals. For much of its history, gamma spectroscopy has been an expensive tool available only to professionals, but in the recent years, companies like Gamma Spectacular have made it more accessible and affordable to hobbyists and amateurs alike. Today, devices like RACID can easily fit in a jeans pocket and still deliver excellent quality gamma spectra, making gamma spectroscopy easier and more portable than ever before. Long story short, we're currently living in the golden age of gamma spectroscopy. There are several methods for detecting and creating gamma spectra, but the most common is by using scintillation crystals. Each crystal type has its advantages and drawbacks, and the choice which one to use really depends on the specific use case. Here are some of the most common ones. Sodium iodide thallium dot crystals are probably the most commonly used crystals out there. They are known for producing high-quality gamma spectra and being very sensitive to gamma radiation. However, they are hygroscopic and temperature sensitive, making them better suited for controlled environments rather than in field use. Cesium iodide thallium dot crystals outperform sodium iodide crystals in pretty much every single way possible. They are more durable, don't suffer from moisture absorption, and produce better resolution. Their only shortcomings are that they are a bit more expensive and have slower light decay time. They are often used in small, portable scintillation devices such as my RACID, which uses a 5 cubic centimeters cesium iodide crystal that has a resolution of 6.5% at 662 keV. Bismuth germanate scintillation crystals are known for their density and high energy gamma ray efficiency. At 662 keV, they typically offer resolution of around 10 to 12%, making them less suitable for gamma spectroscopy applications compared to other crystals. Lanthanum bromide crystals are relatively new to the market, but they quickly gain popularity due to their exceptionally high resolution of below 3.5% at 662 keV. Unfortunately, due to their more difficult production process, they are significantly more expensive compared to more common options such as sodium iodide or cesium iodide crystals. Since these crystals use lanthanum, which by itself is naturally radioactive, they self-generate a characteristic gamma spectrum which has to be accounted when conducting a spectroscopy of low-activity samples. Plastic scintillators are also common and are made out of organic polymers, but they produce very low-quality spectrum, which generally is unsuitable for gamma spectroscopy. Their low price, however, makes them a great fit for detectors meant only for radiation detection. High-purity germanium detectors are a bit different. Instead of using scintillation crystals, they use semiconductors, which results in extremely good resolution, allowing to distinguish peaks that are very close in energy range. While they are the gold standard for resolution, they are less suited for casual use due to their size, high cost, and difficult maintenance, as they require liquid nitrogen to keep them at the working temperature, which is below 110 Kelvin. Depending on what will be measured, it is important to take the size of the crystal into the consideration. For detecting low-energy gamma rays and X-rays, it is better to use a thin crystal, while for detecting higher energy gammas, a thicker crystal would be a preferred choice. For most cases, a crystal size between 1 and 2 inches will be perfectly fine. Photomultiplier tubes are essential, as they convert small flashes of light produced during the interaction of gamma rays with the scintillation crystal into electric current, which is directly proportional to the gamma energies detected. Their quality and performance will impact the final resolution of the gamma spectrum. Sometimes photomultiplier tubes don't come with voltage dividers, which are crucial to supply adequate power to different pins of the tube. Generally, the schematics are easily available online, but if soldering is not your strong side, it might be better to get a pre-made kit or just buy a probe that is already assembled and ready to use. Some small portable devices, such as RACID, use solid-state silicon photomultipliers instead of the photomultiplier tubes found on bigger detectors. This is mainly because silicon photomultipliers are more compact and don't require high voltage to operate, making them better suited for small detectors. I got my scintillator probe from my good friend Geiger, who was kind enough to send me one of his spare ones, and he also helped me with writing and fact-checking this video. If you want to learn more about cool nuclear science projects, then I definitely recommend checking his blog out. I'll leave the link in the video description. The probe itself is a Bicron 2M2/2, and it uses a 2x2 inch sodium iodide crystal, which should give a resolution of 6.8% at 662 kV. Thanks to the large crystal, the probe is very sensitive and it produces around 130 counts per second just from the background activity alone. Inside my LED castle, the activity drops to just 12 counts per second. If you're interested, I'll link to a full spec sheet of the detector in the description below. A scintillator probe by itself is however not enough to start making gamma spectrums. In order to connect the probe to the computer, we need a sound card multi-channel analyzer spectrometer, which will power and convert gamma energies detected by the probe into a usable audio signal. It is here where I would like to thank Steven from Gamma Spectacular for supporting the channel and sending me one of the GS Pro V5 units, which has inspired the video in the first place. The unit feels very nice and solid, and the initial setup was pretty simple and straightforward. It can be used with both single and dual cable probes, and the voltage can be easily adjusted from 300 to 2000 volts, making it compatible with a wide range of different detectors. The only change I would make is to move the USB-C connector to the back of the device, but I guess it's just a matter of personal preference. There are several softwares that can be used with Gamma Spectacular, but since I personally prefer working on Apple computers, I will be using the Impulse software, which has some really great features, such as simple and quick multi-point calibration, and the energy to bin, which makes it much easier to see small peaks from high-energy gamma rays, like in the case of Thallium-208, found in the thorium decay chain. One last thing before we can get started with creating gamma spectra. Radioactivity is all around us, and it is often referred to as background radiation. It can negatively affect the quality of the gamma spectrum and make it harder to see individual peaks, especially when the activity of the sample is low. This is why it is important to try to minimize it. For this purpose, it is best to use LED shielding, as it is extremely dense, making it very effective at cutting background radiation out. At the moment, I have two LED castles. The first one I made a few years ago to use with my Racit. It's basically a paint can that has another smaller can inside of it, and the space between them is filled with LED, which creates LED walls that are 2 cm thick from all sides. While LED is great for shielding radiation, it can actually fluoresce, and this results in an X-ray peak at around 70 to 80 keV. In order to reduce it, I added 2 mm thick copper shielding on the inside of the castle. Here's the gamma spectrum of cesium-137 before and after adding additional copper shielding. Pay attention to the X-ray peak at 75 keV. You see the difference? While this castle works great and I get only 1.2 counts per second with my Racit compared to 45 counts per second outside, it doesn't work too well with my new, bigger setup. This led me to building a second castle that will work better with a larger detector. I made it out of LED bricks that I have casted myself, and while the castle isn't yet finished, I can already tell it works pretty well, and I'm very happy that I can keep the detector inside at all time without the need to remove it to access the sample. In the future, I'm hoping to get some professional chevron LED bricks. Their design eliminates any gaps between them, allowing for even lower background activity inside of the castle. Since LED is toxic, it is best to avoid touching it with bare hands. I've painted my LED bricks to add a layer of protection, which works pretty well, as it is very easy to see when the paint starts to chip off and the bricks need a repaint. So, how does the setup perform? After connecting everything and configuring all the settings, I managed to get a nice 6.96% at 662 kV. Maybe with some extra tweaking I can get the resolution to go even lower, but I'm definitely happy with my current result. While I do get slightly better resolution with my Racit with 6.5% at 662 kV, this new setup is far more sensitive, making it much quicker to build the gamma spectrum and detect low activity sources. Okay, now let's run some gamma spectrums. Each spectrum has been set to a total count of 100,000. Here's a spectrum of uranium ore, radium-226, thorium-232, lutetium-176, cesium-137, potassium-40, americium-241, and krypton-85. Since the day I started learning about radioactivity, I always wanted to be able not only to detect, but also identify different radioactive isotopes. I love both of my gamma spectrometers and testing anything I can get my hands on, and I can't wait to do more experiments and tests with them. My new setup with Gamma Spectacular is now permanently stationed by my desk, connected to my computer and ready to start a new gamma spectrum at a moment's notice, while my RACID travels with me as my everyday carry radiation detector, always within reach. Both of them are excellent devices designed for different purposes and use cases, with my RACID offering convenience on the go, while my Gamma Spectacular delivering much higher sensitivity, better versatility, and better efficiency. I want to thank Steven from Gamma Spectacular once again for sending me the GS Pro V5 and supporting the channel. If you would like to purchase a Gamma Spectacular for yourself, make sure to use one of my affiliated links. It doesn't cost any extra and I get a little commission to fund future videos. Until March 31st, 2025, you can use my code allRad, which will give you 5% off from your order. This code, however, is limited to the first 10 customers, so make sure to use it while it lasts. I wanna hear from you. Do you have a gamma spectroscopy setup? What do you use? Let me know in the comments below. Thank you so much for watching this video. I hope you enjoyed it and learned something new. If yes, please consider giving it a like and subscribing to my channel so you don't miss any of the upcoming videos. Also feel free to check out my coffee page where you can donate a nice cup of radioactive coffee and support my work financially. And remember, stay active.